Alright, in this video I'm going to give you some review of graphing and transformations. Now, I personally found this interesting when I first learned about it, and I thought it was pretty handy and powerful. Alright, so how do we graph functions? Well, you already know, I hope, that you can make a table of a couple of values, right? If you've got y equals f of x, and let's say, like, for example, x squared. So you plot a bunch of points, and you make a table of points, and then you can place those on an xy plane. And I'm sure you've done this before many times, or I hope you have. Now, ideally, if you wanted to be absolutely sure you had the correct plot, you would of course have to do an infinite number of points. But just doing a few gives you whoops, hold on, let me oops, I have to fix my one goes with 1, so let me fix my table there, and then let me put the dot in the right place. Alright, 1, 2, 2, 4. Okay, so if we, by doing a few points, it'll give you an idea what you would get if you did all infinite points, okay? And so clearly, I hope it's clear, if you kept doing this, you would get all the points on this red parabola. And it would keep extending up, so I'll put an arrow like that. Okay? And so there's several different types of functions that I would suggest you memorize their shape. And by memorizing their shape, you'll be able to do a lot of related functions. Okay? What I'm talking about is the building block functions. Okay? Many, if not most, of the functions you will encounter in this class and in calculus are built from a few commonly occurring functions. So that's the good news. If we could memorize the behavior, the graphs of a few functions, then we are good to go for a lot more functions. All right. What are these ones that are the building blocks that show up all the time? All right. Well, we have a linear function, and that's probably the simplest linear function, and that's all we need to memorize for right now. We've got a quadratic. There's a simple quadratic. We have a cubic. Okay, what else? We've got a inverse, maybe an inverse squared. We've got a square root. Okay, we've got a exponential and a log. Okay, if you memorize these guys, you will probably be good to go on most, if not all, the graphing. I'll show you how to build up different functions from these building blocks. Okay, so for right now, I just want you to get the basic sketch, the basic shape of each of these guys. Okay, and yes, I want you to memorize the shape. Okay. That way, when you are graphing something else, you can say, oh, yeah, I know that shape, and then you can just do a few dots to get the position correct, and you are good to go. All right, that's why I think this is powerful, because these few show up over and over again so much. All right, so what do these all look like? The the y equals x, that's a line that goes through the origin, and it's the same distance from the x and y axes at all times, like that. All right. The x squared, that's the parabola that we just drew. That looks like the upside down mountain, we might say. Okay. The x cubed looks like, it looks similar to the x squared. It looks like a parabola on one side, the same parabola. It's a little steeper. It shoots up a little faster. And then on the other side, it's going in the other direction. So like that. Okay? Now the 1 over x is, it comes up, it's a ski slope like this. And then on the other side, it's like this. All right? I encourage you to think about why these have to be the shapes of each of these graphs. That will help you to memorize them. Okay? What do I mean by that? So let's look at the y equal x. As x gets bigger, so that means as you move to the right, the y is going to get bigger. Okay, so that's why you see it shooting up. And then on the left side, as x gets more negative, y gets more negative. That's why it goes down. Okay, let's look at the x squared now. So whether x is positive or negative, it's going to be increasing, and it's going to be increasing really fast compared to the linear because of the square. So that's why you on both sides you have these arms shooting up. Okay, on the x cubed on the right side it's shooting up, but because when you cube a negative you get a negative. That's why it goes in the other direction. See that? So that's how you can kind of not get them mixed up. All right, now the 1 over x. What happens as x gets really small? When x gets really small, then 1 over x becomes huge. That's why you see the graph shooting up to either plus or minus infinity as it gets close to the y-axis. What happens as x gets really big, either a big positive or a big negative? Well, then the inverse gets really small. That's why you see it getting close to the x-axis. All right. We say that the x-axis and the y-axis are the asymptotes. All right. How does the 1 over x squared differ? Well, that one it still gets huge as you get close to 0, and it still gets small as x gets big. So the right side is similar. On the left side, it's always going to be positive, so it's going to end up being like that. Okay? And then the square root is interesting because it has a limited domain. You can't have a negative, you can't take the square root of a negative number if you're restricting yourself to the reals. So we're not going to have a graph to the left of the y-axis. We're going to have something starting at the origin and slowly growing, but not growing too fast, like that. Okay? And then the exponential, that is going to be growing, that's going to be growing very quickly. Anything to the 0 power, anything to an exponent of 0 is 1. So you can always guarantee that it's going to go through 1. Okay, and then it's going to shoot up on the right side. And on the left side, as it gets negative, the exponential is going to get smaller and smaller, so it comes in. So you have the x-axis is an asymptote. Okay? And then the natural log, if you remember that the natural log of 1 is 0, that's how you could remember it goes through 1. And that has a limited domain. You can't take the log of a negative number. And that all that is to say that the graph looks something like this. Okay? So the y-axis is an asymptote, and the natural log keeps growing, but it keeps growing painfully slow. All right? The square root looks like it's growing. It's still growing, but it grows slowly. That's why it looks like it's getting more horizontal. Same thing with the natural log, but the natural log grows slowly, grows even slower than the square root. Okay? Now, how can this help? One more thing. People will sometimes use the terms even and odd functions. When they say an even function, that means a function that is symmetrical. In other words, if you chopped it in half, with a vertical cut at the y-axis, it would be the same on both sides. So what if I asked you which of these are even? Even meaning symmetrical. Okay, I hope you could see that the 1 over x squared is symmetrical and the x squared is symmetrical. So those are even. Okay, there's an algebra way to describe symmetry. Okay, another way to say it is that if I plug in a number into a function, and I plug in the negative of the same number, that will give me the function value will be the same. See that? F of x equals f of minus x. So that's what it means to be even. Okay, I hope I've made that clear. Now, odd is a little weirder, but there's still a pattern there. Odd, let me just first of all give you the algebra explanation. The algebra explanation is that if I plug in negative of some value, that's the opposite sign of the original value. Okay, so f of minus x equals minus f of x. Now, what does that mean graphically? Can you describe it in terms of pictures? Well, you can think of it that if you take what was on the right side of the y-axis, you flip it over the y-axis, then you flip it over the x-axis. So if you do two flips, the right and left piece will be on top of each other. All right. So which ones are odd? Okay. Well, the linear, the y equal x, that one is odd. If I was to take the right piece, if I flipped it over the y-axis, I would get this purple stick. Now, if I flip that over the x-axis, I'd be on top of the left part. So that's what I meant. Okay. The x cubed is also odd for the same reason. Okay. The 1 over x is odd. All right. And the rest of the functions are not even or odd. So you don't have to be either one. All right. Now, the square root and the natural log already are disqualified simply because of the limited domain. Okay? Now, I'm going to talk about transformations, how you can use these to help you graph other functions. All right? So, I showed you what the graph of x squared looked like. Something like that. And I even made a table for you, didn't I? So you can plug a couple of values. All right. Now, suppose I said, now I want you to tell me what the graph, not of x squared is, but now I want you to tell me what the graph of x squared plus 3 is. All right. So imagine that you went through the trouble of making the table all over again. All right. Now, I hope you can see that the long and short of it is you simply have to bump up the values on the right column by 3. Right? That's what the plus 3 will do. 7, 4, 3, 4, 7. All right? So, what does that mean on the graph? What does that mean pictorially? Well, if you increase the y by 3, that's the same as increasing the height by 3. So what that does is it scoots the entire graph up by 3. Okay? So this is important. Now listen to what I'm saying. If you add a number, all you have to do is take that original building block. Remember those functions you memorized? You just take those and you scoot them up. Okay, now what if I subtracted? Okay, if I subtracted, let's say 3, well then you're going to subtract from the column on the right, so that's going to move the whole graph down. Okay, so adding and subtracting a number shifts the graph vertically. Okay, that's very nice to remember that. Okay, that's a transformation. You're transforming one function that you know into your new function. Okay, let's do some other examples. So what if I did this to the parabola? Okay, here's our x squared again. What if I said, now I want you to do x squared minus 2? Okay, no, we already know that. That means you shift down. I'm sorry. What if let's back up. What if I wanted you to do x minus 2 squared? Okay, let's think about how those tables compare. So for the original parabola, we had 4, 1, 0, 1, 4. Now the x's are going to be shifted. Well, here, let me write the numbers here. So when I have a 2, I'm going to subtract 2, so that's going to act like the 0. When I have 1 minus 2, that's going to act like the minus 1. 0 is going to act like the minus 2. Okay, so can you see that I shifted the column on the right up or down? In this case, I shifted it down. Okay, and then the 1 would give minus 1 minus 2. That would give 9, and then 16. All right, so whereas before I had the 0 went with the 0, now the 2 goes with the 0. So why? Because I shifted by 2. Okay, what does that mean for the graph? All right, well, the graph is going to be shifted horizontally. Okay, so whereas before it was centered at the origin, now it's centered at now it's centered at x equal to 2. All right, what if I added 2? So let me do that example. So x plus 2 squared. You could work out the columns and you would see that what happens there is that when you add 2, you move to the left. So now it's centered at x equaled minus 2. Okay, so adding a number to the far right side moves it up or down. Adding or subtracting a number from the x itself within the expression moves it right or left. Okay, are those the only types of transformations? No, they are not. Here's a couple more. Okay, what if I have a function and I multiply the whole thing by a negative sign? Let's see what that does. All right, well, here's the original parabola. So if I was to make my table, that negative sign is going to change the sign of all the y values in the second column. All right, changing the sign of the y value puts it below the x-axis instead of above. So that's going to have the effect of flipping the graph over the x-axis. Okay? Now, what if I instead, or what if in addition to the negative sign, what if I did something like minus 10x squared? Or what if I just did positive 10x squared? Okay, multiplying the y values by 10, clearly that's going to make the heights increase. Okay, so this is going to you could think of this as stretching the graph vertically. Imagine if the xy plane was made of rubber and we pulled it, we stretched it vertically. That's what multiplying by a number does. Now, suppose I multiplied by a small number like 0.1. Okay, that would be compressing it. Okay, so multiplying by a positive number either stretches or compresses it vertically. Okay, and with the negative, you stretch or compress it, and you flip the direction. Actually, I need to make a narrow one, don't I, for this last picture? Okay, And the last transformation I want to bring to your attention is where you have something like not multiplying the whole thing by a number like I did. I multiplied the whole function by 10, but what if I had a function like this, all right, and then what if I changed it by just multiplying the x itself by a number? Let's see what that does. So I'm not multiplying on the right, I'm not multiplying the entire expression by 3. I'm just multiplying the x by 3. Okay? The x squared plus 1 is the x squared graph shifted up by 1. We already knew that. Okay? And what happens when you multiply the x by 3, remember I said that multiplying the whole thing stretched it or compressed it vertically. So multiplying just the x by 3 is going to stretch or compress it horizontally. See? Okay? So if you get those confused, like is it stretch, is it compressing? All right, whenever you start getting unsure of the details, I would go back to making a table. Okay? You just plug in just a few points will make it clear what's going on. So let's see, square and add 1, square and add 1, square and add 1, square and add 1, square and add 1. All right, so let's now do the second one. So let's see, triple it, square and add 1. So triple that, let's start with the 0. Triple that, square and add 1. Triple the minus 1, square and add 1, 10. Okay, 2, triple that, 6 square, 36, 37. Triple that, minus 6 square, okay, 30. All right, so at the 2, it's much bigger. Okay, so so that means that, let's see, so it's clear that the graph is going to be something like this. It's going to be tighter, right? So you can interpret that as if you took the rubber sheet, if the XY plane was made of rubber, you're compressing it horizontally. You're taking the right and left sides and pushing them together. Okay, if you multiplied by a small number, you can go ahead and do that one, and you would see that that's the same as stretching it. Okay. Actually, there is one more transformation I forgot to mention. Let's do that one. That's the one where you multiply the x by a negative sign. All right. So let's say that I had y equal the square root of x. All right. And suppose that now what I did was actually, you know what, let's instead do x cubed. We haven't done that one yet. So the graph of x cubed looks like this. Okay, and now I want to do minus x cubed. All right, so if you multiply the x, remember when you multiply the whole function by minus 1, it flips it over the x-axis. When you multiply just the x by minus 1, what it does is it flips it over the y-axis. Okay, so that's, you would get that graph. Okay, so this is very nice to be able to get all kinds of graphs just from memorizing those few. All right, now what about if they don't just have one of these transformations? What if they got a bunch of them going on at the same time? Okay, something like this. Okay, what you can do here is you can just apply the you can have multiple transformations and you apply all of them. All right, so let's let's think about what the minus does. If the 7 wasn't there, the minus would flip it over the x-axis, right? And then the 7 by itself would shift it up. So we're going to do both of those. We're going to shift it and we're going to reflect it over the y-axis. Okay? Two things. Shift it up and reflect over the y-axis. So the only danger is that you do it like the order, the wrong order. So again, if there's any doubt about what to do, you can simply do a table. Okay, I'm going to sound like a broken record, but I want you to be safe. I want you to get the right answers. So just do a table. Minus, this would give 3, this would give 6, 7, 6, 3. All right. So minus 2, let's see here. 2, 3, minus 1, 6, 0, 7. Okay, so all right, so to me, just looking at a few points, it's clear that what's happening is the graph is like this. Okay, so it was shifted up to the 7, so, and it was reflected. All right, and I just did, I knew it had to be reflected and shifted, and so I just plotted a few points, and it was clear that that's the way it looks. Okay, and it's centered at y equal to 7. All right, so you'll in the homework you'll get some practice doing multiple transformations, and you should be able to do these without a calculator, without any aids except just your memorized building block functions. All right.